Very good, folks. What are we up to? January 2018. January 18. Here in 2026. I'm getting organized, you can see. Rich has other things he had to get to, and so you get me. Oh my. Uh, let's see what we can do. We're going to work around our way around the time zones, starting way off in the east. So I see Dmitri, Wolfgang, and then Eduard to start off, and then I'll probably just go down alphabetically as it shows here in the participants list. I'm Ted Klein. I have something to do with Sarah, but not much. But let's see what we can do here. Dmitri, tell us what's been going on. What are you working on now?
Ted, thank you. Thank you. Today I am in observations 43 gigahertz, and I can show you all process in leaf air. Now I am in laboratory of Sergey, Radio Whiskey 3, Bravo Papa. Oh, yes, I can show you. Just a moment. Just a moment. Oh, Sergey, Radio Whiskey 3, Bravo Papa. Hello.
Hello, wonderful.
Now I am collecting data. This is integration time is not finished. As you can see, Sergey laboratory. He is one of the leaders in EME at millimeters waves, world leaders, and now developing 76 gigahertz system for EME. I can show you his microwave update diploma 2017. You can see his laboratory, measurement equipment, and I can show you antenna in work, 2.4 meter dish antenna. Just a moment. This is second room of laboratory. This is milling. This is bonding machine. Milling machine, and yeah. And you can see antenna unit for Sergey antenna unit for 76 gigahertz. This is Gregory subreflector. And this is transmitter line. Transmitter power amplifier with power amplifier 8 watt. Liquid cooling power amplifier. And this is a receiver with LNA, low noise amplifier, with noise temperature about 180 degrees Kelvin on 76. And this is subreflector. Subreflector, Gregory subreflector, and it corrects. This profile is opposite to the main mirror. This subreflector corrects irregularities of dish surface. And now I can show you the dish. It helps to reduce RMC error of the dish almost in 2 times. Oh, just a moment. I need to dress. I need to get dressed because it's too freezing weather outside. about minus 12 Celsius. It's up to 510 Fahrenheit degrees. And I can show you the dish in observation. 43 years. We set up 43.
This is 18.4.
64. Oh, just a moment. I am upstairs. I'm climbing upstairs to the roof with the this is the dish, 2.4 meters, with 43 gigahertz antenna unit for observations. You can see the receiver, and I can show you feed horn, 43 gigahertz. Now I am in observations of maser line, silicium oxide maser line from Orion KL. Is this antenna now is directed to the source. It's late evening in Moscow, so not like in day in United States. And you can see the dish. In just a moment, I am going down. Now already in laboratory. Just a moment. Okay, I'm again in laboratory. You can see measurement equipment, and I can show you milling machines, precise micron precision milling machine, constructed by, designed and built by Sergey by its own means. For it's all I to show you for today. If some questions, I will be glad to answer.
That was a fun tour. Thank you very much, Dmitri, showing us all the neat stuff. And now we understand how they're all related to each other. So far up on the roof. Thank you for wandering the snow for us. Questions? Questions for Dmitri? I think you covered it all. Well done. That was a fun tour. Thank you for all that.
Thank you, Ted. Thank you.
I do have one question. This is Nils.
Nils, please.
Yes, sir. Coming from Arizona, we're amazed with all that snow. Fantastic. But I am curious, is there any sort of de-icing, or how do you keep the snow away from your electronics on the dish?
Snow. No, it's not snow for today. It's almost not perfect clear, but not snow. Some protecting covering of on feed horn is now on feed horn, but other not special protection because weather without snow, without wind, and it's work well. And offset antenna usually don't collect any snow when in parking position. So.
Okay, thank you.
Right, Dmitri, can I ask a question?
It's Mark
Oh,
here.
okay, okay.
Yeah, very, very impressive lab setup. I was just curious, is how much time can you dedicate to your subject? Is this like 40 hours a week, like a working week, or?
I was building my 43 gigahertz receiving from beginning of project was 2-3 years ago. Designing and building the receiver, and dish development, Sergey dish development was much more longer. It's almost 25 years to this antenna, and continuous working about its accuracy of pointing.
Thank you very much. Very interesting. Great. Thank you.
Again, thank you for your tour. That was great fun. Fun to see everything all together. And best wishes to your helper and assistant and partner right there. Well done.
I had one question for Dmitri. I am just amazed. What kind of active device are you using for 76 gigahertz for your LNA? What kind of active devices are you using for that?
Okay, yeah, I'm just a moment. I am switching to Sergey. I can Chinese die chips in power amplifier and ohmic chip in low noise amplifier. For power amplifier is was built on several 2 watts
four of 2 watts amplifiers, 4 2 watts amplifiers combined for 2 watt amplifiers. So the result is 8 watt. It is enough to get the good echo signal from the moon surface, and the month ago it was the first ever transmitting the signal from me to Germany, and I hope in near future it will be possible to do the normal two-way QSO, two-way communication. It is the main aim of all my activity for the last 15 years. I got the echo from the moon, the first echo, in 2013. But it was the first test. It was tube, TVT, the traveling wave tube, power, and the low noise amplifier is what not was not good. Now there is solid state power amplifier, and low noise amplifier, about 180 degrees, 80 kelvins, 180. Noise figure is 2 dB. It is good for this band. It is good. I mean, it is without cryo cooling without liquid nitrogen. What it is for the temperature, wind,
room temperature.
room temperature, yes.
Well, that's amazing. Do you suppose that you could actually attempt 110 gigahertz for detecting the carbon monoxide line? Do you think that's possible?
Excuse me.
Just a moment. I'm planning for now 86 gigahertz receiver for silicon oxide lines. Maybe carbon monoxide is more for future. For in 1-2 years, 86 gigahertz silicon oxide line receiver for silicon oxide line is planned.
Well, you're almost there. 86. You just need to go a little higher for carbon monoxide. It's amazing. Thank you so much.
Okay.
Congratulations
Thank
on that work. It's excellent. Thank you.
you.
Very good, Dmitri. Thank you so much.
Thank you, Ted. Thank you.
It's a difficult job, but somebody has to follow, Dmitri. I pick on Wolfgang. Wolfgang, tell us what's new with your world.
Well, there's not too much new because I've been traveling over the holiday season, so I'm just back a couple of days, still suffering from some jet lag. But nevertheless, I've been at the telescope looking again at W49 and the water maser there at 22 gigahertz. As you may recall, we are observing this regularly to see how it develops. Since the last measurement sometime in December, there's been not too much change, so I'm not showing anything. There's one spectral line which is still flaring at about the same level. Also, there is some sort of news on the fast radio burst front. There was a detection by the CHIME telescope at the end of December, so we picked up observing that. So far, we have not been lucky to detect any pulse. However, our partners at the Westerbork telescope, they have just yesterday seen something, so we'll continue observing there, hoping to get some results anytime soon, hopefully. And the third element that we're working on, educating ourselves and finding out where the details are, is on the interferometry side. Also, you may recall that we had the first very large baseline interferometry experiment between Dwingelo and ourselves. We want to do some more measurements in the next few weeks. So that's what we are working on. But also we stumbled across some issues with the software-defined radios just recently on the interferometry side. So we're working on that. And that's, I guess, pretty much what's going on right now.
Very good. Thanks for the update. We're working our way westward on the Earth. Eduard, I think, is next, and then we're going to go up to Andrew up in England, and Mark as well.
Hello.
Eduard.
This is Eduard from the Netherlands, so same time zone as Wolfgang. Actually, Astronomy is not that far from where I live, so I occasionally visit there. So yeah, not really too much on my front because these last 2 weeks I finally have a job, so I'm quite busy with that. But still, in my spare time, I've managed to find some time to do some radio astronomy. So not this week, but the week before, we had very cold and snowy weather. So I wasn't really able to do much in the way of radio astronomy. This week has been a lot less snowy, almost like it's springtime here, so warm. And yeah, I did do a new observation of Westerhout 49 as well, just like Wolfgang did. So yeah, again, not really too much change, but I'm still going to show it anyway because there's something else interesting to show. I hope you can see this.
Looks great, nice and big.
Okay, so yeah, we have here my three most recent spectra from December 24th, December 30th, and then January 16th. So that was this week. And as you can see, the shape of the spectrum is very similar. So like you see all the same features. The only thing that is varying is the level, mostly. So there's not a whole lot of variation in the sort of shape of the spectrum or features with respect to one another. So there's two things that you need to know about these water mazes. So first of all, they kind of occur in a small cluster inside the star forming region. And because this whole cluster is so far away, it's like tens of thousands of light years away out there in the Milky Way somewhere, that it's essentially a point source, even for Wolfgang's 10-meter dish. It's really small, but still the distances between these individual maser clouds are actually quite large. They are in the order of, I don't know, maybe some light months or something. So if there's a change happening in one part of this cluster, it doesn't necessarily affect like the other parts of the cluster. So the second thing is that we are seeing sort of two kinds of variability here in this spectrum. So one type of variability is intrinsic to the masers themselves. So these are just maser clouds themselves changing in brightness. And the second type of variability that we are seeing is extrinsic. It's caused by external factors that have to do with the measurement. For example, maybe the pointing was a little bit off, or maybe there were some clouds or some other stuff in the atmosphere, some more moisture that was causing a higher path loss. So this can also cause some false variability. And the question has been how to disentangle these two effects. So one way to do this is to look at the different ways in which these sorts of variability look. So if you have like a pointing error, for example, in the dish, or if you have some more or less absorption in the atmosphere, then that's going to affect all these peaks in the spectrum similarly, like with the same factor. And if the variability is intrinsic to the maser itself, because these masers occur in these clusters and these different clouds are spatially separate, it often only affects like a certain feature or a certain group of features, or at least like not all at the same time. So that could be one way to sort of disentangle these effects. And what Wolfgang and I have seen for the most part is that this feature, if you compare this feature here at sort of 6 kilometers per second to most of the other features, the other features are much more stable, whereas this bright feature, it has brightened over the past few months. So currently, like in the past month or so, it has been sort of sitting at the same brightness with respect to the other features. But because I think that it's worse in my case because my pointing is probably not as good as what Wolfgang has. You see also this sort of level variation on top of all these features at the same time. So I've been trying to experiment with some ways to disentangle the intrinsic variability of the masers themselves from the other effects that have to do with the measurement. So one thing that I try to do is sort of like group these features. So let's say I have a group 1 at -10 to -4 kilometers per second. Then I have a group 2 that only covers this very bright feature, and then a group 3, which is this other small group of features that are above 10 kilometers per second. And I sort of took the average power of within these groups. So if you plot this over the time, it says days here, but that's not correct. It's but if you plot this over time, you get something like this. So you can see that the group 2 has this sharp increase. So this is this bright feature, while the other groups kind of, yeah, they vary as well, but they sort of stay at the same level. And what you can also see is that there's quite some correlation between all these trees. So you can see some points where they all go up and down. And I think that this is mostly due to this part of the other factors like pointing errors, for example, which affect all of these major features similarly. So what I then tried next was to plot the ratio between these groups. So here you can see, for example, that if I plot group 2 divided by group 1 and group 3 divided by group 2, so you can see that this sharp rise in this bright feature. Whereas if you divide group 3 by group 1, so these were like the weaker features, below and above the bright feature, you can see that it mostly stays very similar. So these other features are not really having a lot of variability with respect to one another, but this bright feature has really increased in brightness quite dramatically over the past few months with respect to the other features in the spectrum. So that's basically what this is showing. So anyway, that was kind of what I wanted to show. This was just a quick and dirty experiment. It's not really anything serious yet. But yeah, I'm sort of starting to think of ways to better interpret this maser data to make sense of it. And yeah, if any of you have ideas or suggestions about this, I would love to hear about that. So yeah, that's it.
Excellent. Appreciate all your good work. Questions or suggestions even for Eduard?
I have a question, Edward. As I understand it, usually the astronomical masers do emit their signal directionally. In other words, they're similarly to like what a laser beam would be. So it could be that that some of that variability could be caused by some kind of a either rotation effect or something where the beam essentially is then shifted from the directionality towards us. So is there a possibility that maybe by some detection of a slight Doppler shift or something, you might be able to distinguish any of those features that might be moving away from us in terms of the so you'd see a relative intensity change alongside some kind of a Doppler shift. Is that a possibility to maybe utilize detection for those features to analyze what some of those components are doing?
Yeah, that's a very good comment, I think. Yeah, from what I've read about these masers, so how you can think about them is that they're essentially gas clouds. So they're really not like your typical laser that you think of that is essentially like a chamber with two mirrors at both ends, and the photons are bouncing between those mirrors and essentially like building up a path length that way until you get a beam. And yeah, these masers are just basically gas clouds, so they can essentially emit in every direction. However, the amplification is going to be the most in the longest dimension of the clouds. So, and of course, in nature, these clouds will never be perfectly spherical, so there's always some directional component to it. So that's absolutely correct. And in addition to this, if you have like two clouds that are and if you have two clouds, maser clouds, and one cloud is moving in front of the other from our perspective, this foreground cloud can then start to amplify the maser radiation of the background cloud if they are moving at the same velocity with respect to us. Otherwise, they would have like a Doppler shift with respect to one another, and this wouldn't work. So this is also one way to get a temporary brightening of one feature. But of course, the tricky thing about this is that this would typically only affect like one feature in the spectrum, because both clouds would need to have the exact same Doppler shift with respect to us for this trick to work. So it gets really interesting when you see two or more features that are increasing and decreasing in brightness at the same time, because then there's probably something else going on that has to do with the physical environment of these masers instead of just a simple geometrical effect that you were talking about. So about the Doppler shifts, I am not really sure. So they have been observed in previous masers and maser flare events from what I read in the papers, but unfortunately my Doppler measurements are not perfectly accurate. So it has to do with some limitations of the LNB and the way I deal with the frequency drifting, which is not perfect. But I think that Wolfgang and their team, they have some better equipment. They could actually do more reliable Doppler measurements, but I'm not sure. So you would have to ask them. Anyway.
Maybe I can comment on that. You also have to see, because of these are clouds, they have some turbulence. So you get a Doppler spread within one cloud. So minor changes will be essentially covered by the turbulence and the corresponding Doppler broadening. Also, in this case here, we're talking about masers which are part of a molecular cloud. There's another type of maser which are typically not water masers, where they're circumstellar, that is, they are around a strong emitting infrared star, and these tend to be pretty much isotropic in their radiation.
I see. Well, thank you very much for that explanation. That clarifies some of what I understand regarding their emission. Do appreciate the comment and excellent results on those observations, Edward. Really some detailed work. Fabulous. Thank you.
Thanks.
So much we're learning just from observations. That's fantastic. Well done, Edward. Okay, we're working our way around the world, traveling to the west, now to the UK and I guess England at this point. I'm going to pick on Andy first, and then Mark, please.
Okay, thanks, Ted. Right, so I have a very short thing to show. Where are we? Let's share it. So can you see the presentation starts with calculating LRO H-line tunable antenna?
We see the graphics looking great, nice and big.
Yeah, so good. Yeah. So I've been we've been discussing this a bit in the mailing list for Sarah. So it's just an idea. So first of all, let me just tell you a little bit of a story. So Alex Pettit and Wolfgang here have published some wonderful stuff online telling us how to make various hydrogen line antennae and also antennas. And you can see there, Wolfgang, I've nicked that picture straight out of your H-line document. I hope you don't mind. Because it's a real source of expertise. I don't know what your experience is like, Wolfgang, when you make these things. I imagine that you're there in Astropelia and you get yourself a stovepipe and a cap on the end, and you drill yourself a hole, and it's perfect first time. But when I do things, things don't quite work this way. So and this is just typical of my experience, but the last cantenna I made, and so for anybody who's watching this video, perhaps who's never heard of what a cantenna is before, it's, as you can see in that picture there from Masterpedia, it's basically a can, in this case a piece of stovepipe, but you can use coffee cans, and they have a monopole, a single half of a dipole inside, which acts as the aerial, and the can sort of directs the signal down to that monopole, which is then sent to a receiver through various filtering or amplification devices in the way. And the dimensions are really important to make sure that it tunes to whatever signal you're trying to collect. And in this particular case, I'm trying to get hydrogen line for mapping the Milky Way. That's 1,420 megahertz, 1.42 gigahertz, or 21 centimeter line, as it's often known as. So my experience was this in the last container, which is I used, in my case, a coffee can, And I put a chassis connector, which you can see is at the end of the red line on the 9.3 centimeter there. There's a chassis connector. I'll show some pictures of those in a minute or two. And I put it in, and I cut myself up or soldered the monopole on the inside, which I deliberately made was slightly long, so that I could then tune it practically to get it just right. And I got it to pick up signals, and I had my nano VNA, and the level of the signal was going up, or the improvement of the VWSR was going up, as I trimmed off tiny little bits off the end of this monopole, and it went up, and it went up, and it went up, and then suddenly I trimmed another slight bit off, and the whole thing dropped down through my boots, and was awful again. I ended up having to remove it and solder another one on and stick it back on, and for me, that is my sort of typical experience, probably because I don't do it properly in some way, shape, or form. So my plan here was to try and produce a tunable antenna, which literally you could change the dimensions without having to chop bits off. And then if you got it wrong, you would go back in the other direction until you got it just right. So I started off by sort of following the Wolfgang's advice here and getting one of these stovepipes. I found a bit of aluminium tubing I could get. Then I needed a cap to go on the end of it, and I found a cap which cost me, in stainless steel, and cost the same price as the aluminium tubing, but there we are. And then I started looking up some dimensions to find out what everybody else did. And the SETI League have, so obviously Wolfgang has published his dimensions there, and the SETI League have also published some dimensions that they advise. And so I just put them together on that diagram. And also, I found this calculator online from 3gaerial.biz, where you could actually put in various measurements and find out what that came up with. And then Argus Station there is another SETI League set of calculations. So putting those together, right. This, by the way, sorry, I should say, so the aluminium tube I got, if we go back to this slide here, this 3gaerial.biz on the left-hand side calculator. So I bought a 150 millimeter, 15 centimeter, 6-inch wide aluminium tube, because that's what they're sold as. But when I actually got a ruler to measure the dimensions, it was 150 millimeters on the outside diameter, but the inside diameter was 146 millimeters. So I put that in here somewhere, say 14.6, which I've circled there, and so that gave another slightly different measurement as well, and for what distances and from two important distances shown here on Wolfgang's diagram from the center of the probe through to the back of the antenna, and also the actual length of the probe itself inside are the two really important ones, apparently. So it says, if you read lots of people online. So I put those three things together. We've got Astroperio at 93 millimeters for 150 millimeters. I wasn't sure whether that was outside diameter or internal diameter. And we've got Barry's here at 156 millimeter disc diameter tube, or 88 millimeters. And then we've got a slight difference on this other Argos station one, which is 152 millimeters, but also 88 millimeters from the back. And then, and this is from that 3gaerial.biz, where I just put in a variety of different can diameters and asked what they would suggest. And so in reality, it turned out that those distances that Wolfgang and other people were getting seemed to measure, give or take, with what was coming out of the calculator. And you can see there that what doesn't change is the probe length, which still comes out as being the same length. The distance from the can to the back goes down as the diameter goes up. Yesterday, or either yesterday or today, Alex put a post on the mailing list commenting that the diameter of the probe does affect the length of the probe, but that's not something that I've looked at there. Now, in terms of, so just going aside a little bit, this is the cap that I found to go on the end, and I've got one here, which you might be able to see. And you notice it's it's a push fit cap, the little clippy things that push and hold it firmly. And I thought that was quite neat, because that would then allow me, as in the diagram on the left-hand side there, because it's meant to be for chimney flues, I could push it in, and then I might be able to twiddle it in and out a bit and actually change effectively the length from the inside of the chassis connector through to the back of the antenna, so I could actually tune that distance. But this is just an aside here. We had the hydrogen line group meeting at the beginning of last week, and Andrew Stowski, who's one of our members, has in fact been doing a study where he's actually been looking at the effect of distance from the back, which is on the bottom here on the x-axis, versus the output on the VNA. And as you can probably notice, there isn't really much of an association. So that's just an aside. It may be that all this business of that distance being important isn't as important as it would be said in the literature. But anyway, come back to that. These are the chassis type connectors I mentioned. As you can see, you can drill some little holes and put some nuts and bolts in and hold them on. And then you can just solder a probe on the inside. Work very well as well as the end types. And this is what I came up with as a solution for trying to have a tunable probe. So these brass coupling nuts, you can easily buy them off Amazon or eBay or anywhere else. And then a little bit of appropriate sized copper threaded rod to go in the end, which can then be screwed in and out and actually change the effective length of the whole probe. So I thought that was perhaps a clever way of achieving that outcome. And come back to this now. So here we are. This is, I hope you can see it. So this is the Mark 1 tunable antenna, which is here with the, probably can't see it, but the tunable probe on the inside and the cap that can be varied in its distance here. So I've yet to test it and find out whether it actually works or not. Probably turned out to be a load of rubbish, but still, there we are. While I was about it, to show you this. So this is my attempt at making a choke out of cardboard and silver foil. I was encouraged to do this because in that same hydrogen line meeting that we had, we were, or I felt very motivated because we had an Indian guy who didn't have access to much in the way of funds or anything else. And so he gave us a presentation on how he's made a 1.5 meter dish entirely out of cardboard and kitchen foil that works. So I thought it's just amazing what some people do when they don't have access to the same type of funds and resources that we have. And I thought that was really motivational. So that's it. Thanks very much.
Wonderful, Andy. We encourage all your experimentation. I think your threaded coupler is a great idea. And then others will talk about, oh my, the threaded coupler will be thick, and that'll change things. So the key is give it a try and discover it. Otherwise, we don't learn new things. We want you to learn, gain a scientific prize from your experimentations here. I'm a little concerned about the cap that goes in because, of course, it's on the inside, changing in inner dimensions, which is affecting that waveguide that you're building. So I don't know. Wolfgang, you have comments first.
Yeah, I mean, first of all, the distance of the probe with respect to the back reflector, so essentially that dimension that you are varying, that is or should be fairly uncritical, because you think about it, the probe is supposed to sit in a maximum of the electric field. And since this is a sinusoidal function, it's sort of the top of the sinusoidal function. So the effect should not be that large when you vary that. Of course, there will be an effect. What you could do, rather than when you try to optimize that, what you could do, rather than measuring the reflection coefficient, if you could try to set up a test signal a little bit away with another antenna or so, and then optimize it by using by looking at the received power. Things are different for the probe length itself. The probe length itself is determined by the vacuum wavelengths. And what I typically find, by the way, I'm using the same procedure as you. So I'm making it a bit longer than theoretically, and then little by little cut pieces off and look at the reflection coefficient. And of course, same happened to me. Sometimes I cut off too much and then I have to resolder it again, but that's a good way of doing it. But of course, having the screw is a bit more elegant. So that's perfectly fine. I would not be too concerned also about changing the diameter due to this this cap that you're putting in. It's just a few millimeters, so that doesn't change too much. Yes, it has some effect, but I think this is more theoretical than in actual reality. Other than that, I think that's yeah, nice way of doing it. And I mean, we have built, I don't know how many of these antennas, lots and lots of them for our interferometer, for all sorts of things, as feeds for our dishes and so on. They're easy to make and can be used as a standalone antenna. It's just a very cheap and easy way of doing things because you don't essentially need any tooling. Yeah, that's, I guess, all what I have in terms of comments.
Oh, thank you.
But if I might, excuse me, I get the same kind of problem as Ted. By the way, it's very sunny here and the sky is clear in western Montana, which is very unusual for this time of year. I somewhat put that tunable thing on the net someplace sometime. But anyway, it was interesting to look again at the results of moving the back in and out. There's a small sinusoidal effect in there. If you look at the data, you can see that there's a very small sinusoidal effect, very small with distance, which is, I find extremely intriguing. I think it's in there. If you look at the data, you can put a little sinusoid on that. Yeah.
Wait a minute. Hang on.
Want me to catch it while yeah.
Yeah.
There, look.
I
look.
actually suggested that in the hydrogen line meeting, but
yeah, look at that little sinusoid. That's really neat. I wonder what that's due to. It's pretty interesting. Now, the other thing is the diameter of the probe affects the Q, so that the larger the probe, the lower the Q and the wider the effective bandwidth of the probe. So there's probably some tiny optimum in there somewhere for what we're trying to do, but I think the adjustable thing is the way to go. But then that's my own personal feeling about it. I agree with Wolfgang. The better way to do it is maybe if you look at your tiny VNA or whichever one you're using, and sort of get it close, and then perhaps you can put a source out. A noise source would be interesting with the VNA as a receiver, in a sense, and then you can adjust it for maximum for a maximum at the desired frequency. I think that's a better way to go because it takes into account some other things like the length of the pipe and etc. So yeah, and the cap, I think it's right that the effect of the cap is not the cap diameter change or the change due to the diameter of the cap is not really important. But that little sinusoid is really interesting. I have no idea where that would come from.
Andy, let's go back to that graph. I was at this
Yeah,
presentation as well, but hang on. Don't assume that x-axis is a continuum here. It's actually separated by vertical lines, separating different experiments. If you look at the bottom, there are a whole bunch of 40s, then there are a whole bunch of 50s,
Oh,
60s, because he was actually adjusting two variables, and so they
never mind.
groups. And so I'm not
Never
sure
mind. I
it's
didn't read.
quite as wiggly
Yeah,
as we expect.
yeah.
Beware.
I think you got it, Ted. I'm sorry. I wasn't careful about my observation.
And I this is Adrian. I'd like to add one more comment. I also attended that particular H-line meeting, and what I'd like to say is that I'm somewhat the word's not concerned, but curious regarding the construction of this cantenna. This cantenna is not your standard coffee can or stovepipe antenna. This is a 3D printed plastic printed antenna with a material that has some component of copper in it, and it's then painted with a more conductive paint, but nevertheless, still a sparse concentration of metal in the materials. So you're not looking at a material that has a high density of metal to it. It can't obviously approximate what a solid aluminum or stainless steel type cantenna normally would be composed of. And so I'm somewhat curious as to, for example, Don, you mentioned the Q of the width of the monopole. Well, I'm also concerned about the Q of this particular waveguide.
You're right.
As you know, a lot of waveguides, in order to increase the Q, are even
silver plated. Did we lose you, Adrian? That's a shame. You're right. The at the 1420 megahertz, I don't know what the skin depth is, but for painted on metal or something, I think the skin depth would be questionable. I agree with you. I don't know what you think, Wolfgang.
I have not really tried a 3D printed feed horn. I have done it for a higher frequency, but I really haven't tested it. So I'm only reporting some opinions that I have heard, that really the continuity of the electric layer is not good enough. And also I heard some comments, I can't really judge on that, where they say that the surface roughness is giving additional attenuation.
That's
I don't have any hands-on experience with it. I love to do that, but so far I haven't had enough time of doing it.
You can, for example, that tape and so on, you can get the thickness of it, and you can simply calculate the skin depth at 1420 megahertz for whatever it's made of, and see what, the skin depth is 1 over E of the loss or penetration, if you want to call it by something. I don't know what the exact terminology is. I've forgotten over the years, but the skin depth is quite important. It's like you had the question about the skin depth of the moon when you start doing moon bounce. And the roughness is important too, although it's usually talked about in terms of something like 1/10 of the wavelength, or even smaller than that. But yeah, because when you get a rough surface, you begin to get a specular reflector, and so the seems to me you'd have some kind of funky mode confusion going on depending on how rough it is. I have no experience with that, so it might be fun to do, but I think the bumps would have to be pretty good size. but I'm sure that the skin depth needs to be calculated for things like using tape and so on. I mean, apparently it's good enough if you want to use aluminum foil. Question might be, do you use heavy duty aluminum foil or do you use regular aluminum foil? What would be the difference? So with that, I'll shut up, except to say that I have no new thing. I'm waiting for spring.
Very good. Interesting discussion. I don't care what they say. I want Andy to do the experiments, discover something new, and surprise us all. Sounds
Well,
great.
I agree. It's in the end with this probe business, exciting modes in the waveguide is a black art. You will not find it written anywhere with any kind of clarity. And it has bothered me for something like almost 30 years. And there's still no clear, obviously, there's no clarity anywhere, even when you have an AI to try helping you.
There
So
you go, Andy.
keep
Figure it
on
all out and make Don feel better. That's good.
keep on diddling is my is
All
my
right.
advice. Measurement is king, as Sabine has it.
Thank you, Andy, for that presentation and all those comments. Very good. We're going to keep working our way westward across the country. Mark, you're over there in the UK as well. And then I wanted to finally get to Tom. He had his hand up half an hour or an hour ago. We're going to go to Mark at this point, please.
Hi everyone. Yeah, I'm sorry I've not got anything as impressive as Dmitri and what's his name, Eduard and Andrew have done. I received my Super SID on the 8th of January, and I've been messing around with the sound card on. I bought a Sound Blaster Play 3, and I didn't realize the frequency limitation. So then I bought this StarTech card last week, and I'm just trying to work out, get the configuration file working. I've built this antenna, 187 meters of 18 gauge copper wire. Yeah, I'm just trying to make that all work. I've also installed Steve Burrell's Python program, and I've been running that Super SID from Stanford. Yeah, I've got one question. People may be able to help me regarding uploading data to Stanford. There is a link. I just remember it ends in data browser, and you can see different dates, uploaded data. How do you actually, if you want to go back, download the data. If I wanted to download something, does anyone know how to do that? Because the links don't work. If I just take, not screenshots, but if I just Control-C the whole page, I get a mess. I'd just like to be able to replicate a chart or two from data that other people have uploaded.
This is the place to ask those questions, but I don't hear any answers this time. And then, of course, there's that SID email group. So good luck with that.
Yeah. Okay, I'll try the Google groups, the SID groups.
But you're asking the right questions and exploring the right world. This is the hobby we learn by doing, so this is good.
Yeah. By the way, one general question concerning electrical interference. I don't understand much about radio, but at these very low frequencies between whatever it is, 0 and 30 kilohertz, what kind of signal do I expect to see? It looks really noisy again. Lots of what do you call it? Just a very noisy shape.
Well, we know that there's a different effect during the daytime, during the night.
Yeah.
So one of those, I guess, is much noisier and not
But
particularly.
if you look at some of the signals on the Stanford database, they look really clear. You know, the submarine signals so obvious, but when I run my system, okay, I'm doing it at home, and I of course I did see a huge difference between when you orient the antenna. I understand the plane of the antenna has got to be in the direction of the longitude of the transmitting antenna, because if you make it at right angles, the signal decreases quite a lot.
You had lots of interference problems at higher frequencies as well, and
Oh yeah.
I don't know why it wouldn't be problems again at low frequencies. That's even easier to create. Andy, you had some comments?
I thought the lower frequencies it's more immune to interference, because I've understood this is only looking at the magnetic part of the signal and not the electrical. Is that right?
It's not clear to me what the real difference there is. Why not have magnetic interference as well? It's just electromagnetic waves running around.
Okay.
You have to find a collection of SID experts compared to us.
Right.
I mean,
And
one thing to say, Mark, is that I've got both the Super SID and I've got one of the UKRAA devices, and certainly with the UKRAA ones, where we're using radio SkyPipe, we tend to run them with averaging, because SIDs, you've got quite a bit of time that you can average over without too much of a problem. Anything up to about half an hour to smooth it out. So actually anything that where it just puts the signal on a moment by moment basis, and the Super SID is presenting it usually every 5 seconds. Plus, it's not unlike the UKRAA ones, which have gain control within the device. You haven't got that on the Super SID, where the price you pay for that, that wide bandwidth is to just have what comes, as it were. I know there is some amplification that's occurring in the Super SID, which is what it's there for in the first place, but it's pretty much unfiltered.
Okay. Yeah, I'm sorry, I don't have anything more dramatic to contribute.
Yeah.
Well, you need to go off and make all that happen. That sounds good.
Absolutely.
Thank you, Mark. Keep working on it.
Yeah.
All right, now let's see. I think we've kind of walked through all the folks who were far to the east, and it's very late at night in that places. We're working our way over here. First off, any other folks outside the U.S. do speak up. We've had folks come and go, but hooray, we're taping this. They can see it later. Tom, you had a question or a hand up long ago. I apologize. We're finally getting to you. Let's do you first, and then I'm walking down the alphabet. I guess next is Adrian. Let's go. Tom?
No, the reason why I raised my hand there was I wanted to inject a comment, kind of acting like I was rich, and telling people to go to the Sarah Help Desk, which is what he wants to call the Google groups, and also to make note of the Super SID Google group for looking for answers. So that's all I was going to say there, and someone beat me to it. So I just, like I say, point that out as a way to ask questions and maybe get help.
Thanks, Tom. I'm aware of that. Thank you.
Well, good. We're thinking along the same lines. Thank you. Now starting alphabetically, we're going with the folks that are still here. Adrian.
Yes, hello. Well, I really don't have anything much to present. I've uh, I've done some little climbing out on a backyard satellite antenna that hasn't been used for a while, and trying to convert that for H-line reception, and had to clear out some bird nests and so forth that had been inside of the drive mechanism for the antenna, and so that's about pretty much what I've been doing. The weather here had been pretty lousy for a few weeks, but now it's become typical Southern California weather. So I believe it's almost 80 degrees and sunny, so it's more conducive to being outside and doing things. So that's kind of the on the to-do list. But other than that, um, I've never really seen that, but I've been losing the Zoom contact today several times, and just curious what was going on. But I guess it's back. But I lost a little bit of the conversation on the comments that we had for the depth length of the antenna and so forth that were being discussed. So I guess I'll go back and listen to that on the recording. In any case, that's pretty much it.
Glad to hear the progress, Adrian, and rubbing in the nice weather. That's nice of you. Good. Uh, good luck in so many ways there. The recording has been continuous here, so I think there's hope. We're working our way down. Dennis is next, and then I'm going to skip all the way down to Rick. Dennis, please tell us what's new.
Okay, Ted, thank you. Thank you guys. All very interesting. I'm absorbing as much as I can. It's sunny out here in Northwest Washington right now, cold but sunny. I think we've really lucked out compared to the rest of the nation, especially the Midwest. So anyway, I'll let you continue and I'll continue to listen and enjoy. I'm nothing else to offer right now. Thank you.
Very good. We appreciate all participants. Andy has put something in the chat all about if you haven't had enough here, there's even more. Andy's hosting things as well. Wow. Now hang on. I think we've touched everybody. Oh, I'm sorry, Rick. Pardon me, Rick. You've moved way up high in the alphabet. What's new with you, Rick? You're busy with DSES.
I am. Right now, I'm working on a precision time and frequency workstation for DSES. And much of the equipment was donated by one of my commercial customers. And it's essentially the same system that I install at NASA VLBI and VGOS sites around the world. So it lacks hydrogen maser. We're using a HP 5065A rubidium instead, but otherwise it's pretty much the same thing that you'll find at telescopes like Westford and Cokie Park. So that will upgrade DSES's capabilities tremendously and provide it with a set of standards that would allow it to participate in VLBI activities in the future. Right now, we're working on a particular program that I'm not at liberty to discuss this week, but perhaps next week I will. I've been asked by the sponsor to hold off until they make announcements about it. But it's all, and this weekend I was down there yesterday in Haswell. Alex says been testing an 8 gigahertz package to see A, will the dish work well at 8 gigahertz? And B, can we use the 8 gigahertz as a higher precision calibration for our azimuth and elevation and other things, which is what was going on this morning. I got some pictures because I wasn't down there this morning, and it looks like it's working okay so far. And we're going to use that for deep space work for monitoring deep space satellites. There's a number of people who are interested in that. And then we have a new package being prepared for 2.2 gigahertz, which is also for satellite detection, not so much astronomy. But then we're going to put we're making some other modifications which will help with improving our performance, although our performance is very good right now on the drift scan project. The last set of data that was analyzed by Ted looked pretty good, so I put it up on our website. Anyone who wants to see how well that's working now can look there, but we haven't begun the full drift scan activity because I want to try to duplicate or maybe improve on what we sent to Ted the last time using a better SDR, the B210. And if that works, then we'll begin a full program of drift scanning at all elevations from plus to minus 20 degrees, which will take us 40 changes of positioning of the dish when we park it. And given that we only go down every couple of weeks, that ought to keep us busy for a few years. Anyway, so we've been very busy. We haven't done any new pulsar work lately. Some of the people involved there have had medical issues to deal with. So I'm hoping to get back down there and do some more pulsar work soon. We've installed yesterday a new fiber optic line with 6 fibers in it from the dish to the control center, and that will be extended all the way up to the feed. Some of our new feed packages have all of the hardware, including the computer, in the feed, so that to minimize losses and variabilities, and we just bring the data down on these fiber lines. So now we have 2 high quality analog LMR 600 lines, and these new 6 lines add to another line we already have. So we have 7 or 8 lines of fiber running out there now. So there's a lot going on, and boy, we can sure use some more volunteers. Back to you.
Thank you, Rick, for the update. You and I were trying to work Ezra collecting data using an NSB210. Has any experiment occurred there on your side?
No, that's what I just said.
Yeah,
I
okay.
haven't switched. The B210 is there, hooked up, connected. All we have to do is change the driver from the unit we're using. They're both connected by USB simultaneously to the computer. So all we have to do is change the driver and we can activate the V210, but I haven't done it because I've been very busy getting this time and frequency palette ready to ship.
Okay, very good.
I have
Let's work
I have a
together.
quick question
Adrian.
for Rick. This is Adrian. I also attended the DSES meeting where Alex was describing what he was trying to do this last weekend, and so I'm just kind of curious in terms of the beacon that he was using, and there was some discussion about how far away that beacon would be able to be placed, and then the signal picked up by the antenna. And I'm just curious if you know what was the distance that was being able to listen to the beacon from.
I believe the work they did this morning, it was about 10 miles south. In all directions, we can go about 5 miles. If we go beyond 5 miles, there's certain directions where we still have a clear path. Other directions we have, we're in a little bit of a bowl topographically, so some directions you go over the ridge. Of course, you can't hardly see the ridge. It's not that big. It's pretty flat out there. But anyway, in some directions, the answer is 5 miles, in some directions 10. I think they managed a 10-mile south today. I have the picture on my cell phone, but it's not on my computer yet, so I can't show it to you. But yeah, I think it depends on the azimuth, how far you can go.
So they were able to detect the beacon because as I understand it, that was like what, sub-milliwatt output from at 8
Yeah,
gigahertz?
yeah, I believe right. It has I think 400 milliwatts, but we use a 10 dB attenuator to get it down to 40 milliwatts, and that's plenty because that gives you about a 80 dB
Wow.
signal. Well, at 8 gigahertz, we're doing this at 8 gigahertz. We're talking about a half a degree, a tenth of a degree beam width. Even if the antenna turns out not to be very efficient at that frequency, it's still, 10 miles is not very far away. And we're trying to make something that will receive the Voyager spacecraft. So
Right.
40 milliwatts is plenty. And the beacon, I was playing with the beacon yesterday. It's really nicely done. Alex did a great job. It has a generator that can do most any frequency up to a couple of 2 or 4, I think it's 4 gigahertz. But to get
Right.
up to 8, he had to add a doubler and
Right.
and a filter. So it actually has 2 outputs. One that's goes 0 to 4 gigahertz, and you just put an appropriate small antenna on it for that, like our 1.6 or 2.2 if we want it. So it'll be a beacon for all those lower frequencies. And then for the 8 gigahertz that we're doing now for the Deep Space Network, it has a separate output that has a filter and a doubler and so forth. So yeah, it's a beautiful little thing. It has a little eyepiece on it, a little eye telescope, so you can sort of point it in the general direction of the dish.
Yeah, that's brilliant work by Alex. Well, fantastic. Congratulations. Then I'm looking forward to. I guess you're not able to talk about the Artemis thing right now, can you?
What?
Can you mention that?
I don't know what you're talking about.
The,
I
the
couldn't
Artemis?
possibly know what you're talking about. If I knew what
Okay.
you were talking about, I'd have to kill you.
Okay. I understand. Thank you.
We're on the edge of data here, yeah. All right. I went through the list here. Did I do it right? Did I give everyone a chance? Going once, going twice? Very good. We're going to cap it off here at an hour and a half. Thanks very much, everyone watching the video this long. Well done. And but now starts the after party.